I am in the exercise book on page 31. This is the exercise set for lesson 2.3 on counting techniques. So exercise book, page 31. Number 1. A floor is to be painted with 5 concentric rings. The colors to be used are red, yellow, green, blue, and orange. How many different patterns could be created? So first of all, let me explain the concept of concentric. Centric means circular, and concentric means this. That's an important word to know. They don't tell me that the circles are equidistant, meaning that they're all the same distance from each other. So I'm just drawing concentric. 1, 2, 3, 4. 1, 2, 3, 4. We need one more. So would you say in this particular example that the order is going to matter? It will. For example, you could choose to paint this circle yellow. You could choose to paint this outer circle yellow. You could choose the order that you want. So a permutation will work here, but so will a factorial. You could do either way on this one. So let me write it this way. Let's go this way. How many rings are there? Well, there are 5. And how many colors are there? There are 5. So when you have the same n value as k value, in other words, here's the n and here's the k, when those values are the same, you can just do a factorial. So you can say 5 factorial and do that on your calculator. It's going to be all clear 5 shift 3. You may have that one memorized by now, that 5 factorial is 120. You can also use the permutation formula. If you just forgot and you didn't realize that you could do factorial, this is always going to be the case when you have the same number for n and k, you can do the factorial. So we have n factorial over n minus k factorial. That is because this bottom term will always be 0 factorial. So n factorial is 5. And then on the bottom we have 0 factorial. So we'll have 120 over 1, and that is 120. So I like answer B as in boy on this one. I also like that problem. I think I would very much like that floor, although it might give me a headache. You could also do this longhand. Just remember what 5 factorial means. It's 5 times 4 times 3 times 2 times 1. 5 fours are 20. 20 times 3 is 60. 60 times 2 is 120. And 120 times 1 is 120. So that's another option to get the answer, however you want to do it. You could do the permutation on the calculator. It's entirely your decision. All right, number 2. And while I'm thinking of it, let me just go ahead because I'm going to need these boxes for my calculator. Let me go ahead and draw them and copy them, and then I won't ask you to sit and watch me do that over and over and over. I'm going to go ahead also and put in the buttons that are constant. This is for permutation. We will be looking, I think, at some combinations as well, but I'll deal with that when the time comes. So these are calculator strokes for the Casio FX260. And we will always start with all clear. We will always end with equals. This will always be the N value. Then you will shift. This will always be the K value. And then depending on permutation or combination, that other box will change. So let me copy that again. Okay, to do this one on the calculator, you would put in the N value of 5. You're doing a permutation, so this is shift 1. And your K value is also 5. Let me just check that. 5 shift 1, 5 equals 120. So that's yet another way to get the answer. All right, number 2. Jesse is trying to determine which rides to go on at an amusement park. He notices that there are 3 roller coasters, 3 merry-go-rounds, and 2 fun houses. Jesse calculates 3 plus 3 plus 2 is 8 as the total possible choices if he wants to ride one of each type. Jesse has made an error. What is the correct number of possible orders? Well, we could definitely do a tree diagram here, but remember, whenever I can do a tree diagram, I can also use the FCP, the fundamental counting principle. And this will tell me also the error that Jesse made. I can already tell you what it is. You can tell me, I bet, too. Jesse was supposed to multiply to find the combinations. So he should have said 3 roller coasters, 3 merry-go-rounds, and 2 fun houses. So 3 threes are 9, and 9 times 2 is 18. So there are actually 18 possible choices, and I like answer D on that one. I will check these at the end of each page. I started to say remind me to do that, but you can't remind me, can you? Hopefully I will remember. Number 3. Which number represents the total number of ways to order 6 people in a line? Well, you can do a factorial or a permutation. With permutation, they use the word order, so order matters here. You have 6 people and you have 6 places, and anytime you have that particular pattern, you can just do 6 factorial, or whatever the value is, because the N and the K are exactly the same number. So 6 factorial, let me just put it right up here. That is the same as 6 factorial. And 6 factorial is 6 shift 3 equals 720. So there are 720 different orders that you could use for that problem. So I like answer E. You could do the permutation formula and get the same answer. It's just a little bit longer. All right, number 4. ClockX sells watches in men's and women's models with small, medium, and large wristbands. A wristband can be made of cloth, metal, or plastic in a choice of black, green, or ivory. How many different ways can you order a watch? Well, I could do a tree diagram, or I could do the fundamental counting principle. So I'm going to set this one up as gender. You choose a men's or women's. Then we have size, small, medium, large. We have material. And we have color. So when selecting a watch band, when selecting a watch, you have 4 variables that you have to consider. And the counting principle tells us that we multiply to get the possibilities. So in this case, gender is male, female, so there are 2. That's called a binary number. Size is small, medium, and large, so we have 3 choices. Material is cloth, metal, or plastic. And color is black, green, or ivory. So the fundamental counting principle tells us to multiply. You can do this on your calculator just fine. And so here's 18, and then 18 times 3, that's this 3, that's this 3, is 3/8 are 24 to 54. I'm going to double check that because I don't trust myself. So all clear, 2 times 3 times 3 times 3 equals 54. So there are 54 different possibilities for this one. So I like answer C on that one. And let me turn to the back of the book and we will check these problems. This is page 31. I went too far. All right. Number 1 is B as in boy. Good there. Number 2 is D as in dog. 3 is E as in elephant. And number 4 is C as in Charlie. So good, or so far, so good. So good so far. All right, let's look at number 5. This will be on page 32. And I think I can just keep going on this page. Number 5. I will make this notebook available if you'd like to print it to keep in your notes. But if you're writing things with me, you should be just fine on that. You flip a coin, choose a card from a standard deck of 52, and spin a 4-color spinner. How many different outcomes could there be? Well, again, the fundamental counting principle will help us here. And we will have the coin times the deck of cards. I'm just going to call it a card. Times the 4-color spinner. So when you flip a coin, it's either heads or tails. There are 2 possible outcomes. From a standard deck of cards, you have 52 possible outcomes. And from a 4-color spinner, you have 4 possible outcomes. The fundamental counting principle tells us to multiply. So we have 104 times 4, and that should be 416. Let me double check. All clear. 2 times 52 times 4. And so I like answer D on this one, as in delta. I could draw a tree diagram, but I would have to put 52 cards in there. I don't want to draw that tree. Number 6. The Funny Face Kit advertises that you can make more than 1,000 different funny faces. Which is the only kit below that lives up to its advertising? So the first one, we have 8 pairs of eyes, 10 pairs of ears, 4 noses, and 3 mouths. Do you want to draw the tree on that one? No. Trust me, you don't. The fundamental counting principle says that I can just multiply that. And I'm going to use my calculator to get 960. 960 is less than 1,000, so that is not the answer. In B, we have 3 pairs of eyes, 4 pairs of ears, 10 noses, and 6 mouths. I can already tell you this is not it because this much is the same. And 6 is less than 8. So this is going to be even less than 960. But let's do it the right way. So we have 3 times 4 times 10 times 6 is 720. 720 is less than 1,000. This is not the answer. This is a weird question. I'm just picturing this in my mind. 7 pairs of eyes, 3 pairs of ears, 10 noses, no, not 10 noses, 7 noses, and 6 mouths. So 7 times 3 times 7 times 6 is 882. Still falls short of the 1,000. Remember, this is an exercise book. They're wanting us to build our math muscles. This one looks pretty good to me because that 14 is a big old number. But the 2 is a very small number. So let's see what we get. 2 times 14 times 5 times 8. Okay, this one looks pretty good because 1120 is bigger than 1,000. But because I know that I make mistakes, I'm going to try the last one. 5 times, 5 times, 5 times, 5 times. Okay, so this is the same as 5 to the 4th power. If you didn't want to type all of that in, you could use your exponent key. I think I will. So 5xy4 equals 625. And let me give you the keystrokes for that just in case you don't know. Because we're exercising here. We're not doing a test. The answer we're looking for is D. But let me show you those calculator steps for this one if you want to do 5 to the 4th power. So you're going to always start with all clear. You always end with equals. That is a very good habit to develop, especially on this Casio, because it doesn't allow you to see what you've already typed in on screens before. I think I have too many boxes, but that's okay. So all clear, 5, no, I have just enough, xy, 4, equals 5 to the 4th power equals 625. This is the wild card key here. This is the exponent key. It sits just above the C key, the clear and all clear. And that will do these powers for you without having to type in so many multipliers. But anyway, number 6 is D as in dog. Number 7. Derek can wear any combination of a shirt, tie, and pants to work, but he only has space in his closet for 15 items total. In order to have as many different outfits as possible, how many ties should he have on hand? Okay. Let me think here. 15 is the max, so we're limited by the 15. Let me approach it this way. He can have 15 items total, and he wants to have shirts and ties and pants. And remember, and means multiply. Okay? So what if we let him have an equal number of them all? So let's say 5 shirts and 5 ties and 5 pants. Let's see what that would be. That's 5 to the 3rd power, or 5 to the 3rd power is 125. Okay, just to be sure, I'm going to check another option. I want to show you something here. So let me just copy that. I'm too lazy to write it again. And that's really all it is. I tell myself that I don't want you to have to sit here while I do it, but I'm just too lazy to do it. Let's say that he did 10 shirts and 3 ties and 2 pants. So you think by increasing the number of shirts or ties or pants, whatever, that you could maximize the number. So let's see what we get. 10 times 3 times 2. That's just 60 different combinations. So in order to maximize the number of outfits, the number of combinations that he would want, it's better to have an equal number of items than one big number. That's just kind of a general rule of thumb. So that's how I knew to go for this combination. It's just a matter of experience with these problems. In this one, 10 plus 3 plus 2 is 15. He could have that many items. But by limiting the ties and pants, he can only wear 1 pair of pants at a time and 1 tie at a time. Or he could, I guess, wear more than one, but that doesn't fit the problem. It's better to spread them equally than to really stock up on one, if that makes sense. So I like answer... What do I like? 125. Oh, how many ties should he have on hand? So they want to know in the maximum number of combos, he would have 5 ties. And I like C as in Charlie on that one. It's not the 125 we're after. It's not the number of combinations. It's the number of neckties that he could have. Okay, number 8. I'm going to try very hard to do 1 video per page because that is so much easier to upload. Coffee from the Coffee Crew comes in mild, medium, or bold roasts, with or without milk, and with or without sugar. Oh no. Draw a tree diagram to show how many different ways you can get your coffee at the Coffee Crew. What is the total number of possible orders from the Coffee Crew? Well, because it says to draw a tree, I'm going to. But if it didn't say that, you know what I would do. Not that. Sorry, I thought I still had it. I would do the fundamental counting principle. But they say specifically that we have to draw the tree. So let's do that. I've had students who love to draw the tree, so hopefully you enjoy this. We can get mild, medium, or bold roasts. A good rule of thumb, if you have a choice, is to put the one with the most options first, and your tree will be a little bit easier to draw. Mild, medium, or bold roast. Now, I'm going to work this both ways. So, on the fundamental counting principle, we choose the roast type. And that's going to be 3. And then the next thing we have to choose is the milk. You can get it with or without. That's a binary number. It's 2. So I'm going to say milk and no milk. I can tell you right now that is the option I would choose. I would say mild roast with milk. So I would follow that track. And rather than write this over and over, you can get medium roast with milk or no milk. And you can get bold roast with milk or no milk. So how many choices do we have right here? 1, 2, 3, 4, 5, 6. And notice over here, what is 3 times 2? 6. So the tree diagram is showing me how this formula over here works. And then we have to choose sugar. And you can get sugar or no sugar, so you have 2 options. And we're going to say 6 times 2, that will be 12. So I believe I should have 12 branches when I'm done. So sugar, let me close that gap just a hair or that won't fit. If you can't get it to fit, close the gap in your tree and it'll fit a little better. So sugar or no sugar. And let me just take a quick picture of that and bring that into each of these options. And you can see those 12 branches coming to life. Let me count them for you. I'm going to use a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 combinations, possible orders, and you can do that with the tree or you can do it right there with the FCP. But either way you do it on the test, you'll get the right answer if you do it correctly. And I like D on this one, as in delta. Alrighty, number 9. The test-taking tip on here is worth noting. If you get confused when working with permutations and combinations, try drawing a tree diagram or making a chart. Then read the context of the question carefully to see if your answer makes sense. Okay, number 9. Anatolia can choose from 105 different outfits. She has more tops than skirts and more skirts than pairs of shoes. How many tops does she have? All right. Let me think just a minute. We're going to need the fundamental counting principle as our base here. Do I want to go that route? No, I don't. Here's what I do want to remind you of. The fundamental counting principle says to do what? Multiply. So this problem is dealing with factors. It's dealing with, if you know how to factor a composite number, this is what we're getting at here. This is one reason that you have to learn to factor in math class. So what that means is this. We're taking her skirts. Let's start with tops. Her tops times the skirts times the shoes, pairs of shoes. And that number has to multiply up to be 105. So we are looking for 3 factors. I didn't mean to mark it out. I meant to do this. Okay. The iPad and I are about to have a problem. All right. These are 3 factors that will make the 105. So here's how I'm going to approach it and hope that it works out. This is a tough question. I'm going to draw a factor tree for 105. So what are some ways that I can multiply to get 105? Well, I know it ends in 5, so it's divisible by 5. What is 105 divided by 5? It should be 21. Okay, so this will be 2 factors that give me 105, but we need 3 because we have to have tops, skirts, and shoes. So which one of these will break down further? Well, it's 7 and 3. So 7 times 3 times 5 is 105. Those are the 3 factors, I think. I'll have to read the problem and see if it fits. But these are 3 factors that could work. So let me go back to the problem. It says that she has more tops than skirts and more skirts than shoes. This will work. She has 7 tops. That's more than 5 skirts. That's more than 3 shoes. They have to be in the correct order. More tops than skirts, more skirts than shoes. And the question is, how many tops does she have? So I like this number for the tops. And this is going to be letter C. That's a good question. It's hard. It's different. I don't think I've ever seen one quite like it. And I'll have to check it to be sure that I haven't done something crazy. But I believe that's going to fit for us. All right, number 10. Sarah's Sandwich Shop normally offers beef, chicken, or veggie sandwiches with American Swiss or cheddar cheese on whole wheat pumpernickel or rye bread. Today they're out of Swiss cheese. How many sandwich choices does that eliminate? Ooh, this is a good one. We could draw a tree diagram. And I think I'm going to. You're probably saying bad words at me right now. Let's do it right here. You don't have to do this. Remember, you can print my page if you are so inclined. So I'm going to come right over here and try to fit this tree in there. Is that going to fit? Okay, let me try it right here. I can write small. All right, the first thing you have to choose is the type of meat or filling that you want on your sandwich. So you can get beef, you can get chicken, or you can get just veggies. I love Subway's veggie sandwiches. Then you choose your cheese. And each one of these has how many choices for cheese? 3. We have American. We have Swiss. And we have cheddar. No pepper jack. That's what I would choose. Y'all, I'm hungry. I'm going to have to go eat something. Okay, so here are the cheeses that could go with chicken. And then here are the cheeses that could go with veggie. So at this point, we have 9 possible choices. 3 times 3 is 9. 3 types of filling, 3 types of cheese. And then you have to choose the type of bread you want. And this is where it gets hard for me to think. This really starts to get to me after this point. So you can choose whole wheat, pumpernickel, or rye. That's a funny word, isn't it? Pumpernickel. Okay, let's make a copy so I can just duplicate it. And you can see how complicated this diagram is getting in a hurry. I can't even fit it all in here. Can you imagine if this went more than 3 levels? Look at that mess. So this is not the best option to do this. I'm going to go back and just simplify it down a little bit. What this question, though, is saying to us is that we need to eliminate the Swiss. We need to take the Swiss out of the equation. And what does that do to the overall tree diagram? Well, you can't attach one to Swiss because there is no Swiss. So you can see just visually, this is not how I'm going to solve it, but you can see how much simpler it gets just by taking out one of the choices. You actually could see the answer right there if you just count those branches. So there's 3, 6, 9, 12, 15, 18. But those are the choices you have left. The question is how many choices were eliminated. So here's how I would do this question if I had it on a test. This is not the way I would do it. I would use the fundamental counting principle. And I would say that on a normal day, when they have Swiss cheese, you have 3 choices of filling, 3 choices of cheese, and 3 choices of bread. So that's 3 to the 3rd power. 3 times 3 times 3 is 27. But on this particular day, when there is no Swiss cheese, you have 3 choices of filling, 2 choices of cheese, and 3 choices of bread. So 3 times 2 is 6, and 6 times 3 is 18. So you're looking for the difference between 27 and 18, and that's 9. The question is, how many sandwich choices does that eliminate, not having any Swiss? So I like C as in Charlie. You could absolutely do it with a tree diagram if you are so inclined. But to me, I would much rather do it with the fundamental counting principle. It's going to be a lot easier on my eyes. All right, let me check these. And if they're not right, y'all, I just give up. But we have seen that I do make mistakes. So, page 32, starting at number 5. Here's 5. They say number 5 is D as in Delta. 6 is D as in Delta. 7 is C as in Charlie. 8, D as in Delta. 9, C as in Charlie. 10, C as in Charlie. And we haven't done number 11 yet. I think I'm going to put number 11 right here. I still have some space. In case you want to print this file, I want to keep it as small as I can. This is page 33, number 11. Oh, I'm supposed to stop the video. I'll see you back in the next video.